Before we going to prove Riemann integration, we have to know some definitions. It is uniformly continuous definition. In order to know that, I will first revise what is the definition of continuous function. Continuous function definition is like that. For all epsilon greater than 0, there exists delta greater than 0 such that 0 greater than or equal x minus y greater than less than delta, which is implies fx minus fy less than epsilon. This is the normal definition of a continuous function. It means if there is a delta like that, actually this part is not needed because in a continuous functions you know that fx equals fy, the function value of y should be equal to fy. So then if when x equals y, we can conclude that fx minus fy is become fy minus fy, and this part becomes 0, and the total statement stay true when x equals y. So this part is not needed. This is the normal definition of continuity. It means when this happens, this function is continuous at y. So let's take a function inside an interval a and b. Some function inside a and b. If this happens to every x value in this interval, we can conclude that this function is continuous in this interval. It means we can slightly modify this definition like that. For all epsilon greater than 0, for all y belongs to a b, there exists a delta greater than 0 such that x minus y less than delta implies fx minus fy less than epsilon, which means for every y value inside this interval, this satisfies the definition of a continuous function inside this interval. It means this function is continuous in this interval. So this is the definition. When this happens, we say this function is continuous on a, b. When there is a special case, called uniform continuous. Uniform continuity, it is slightly different story. When this definition, we can have different delta for different values, different x values in this interval. But the continuous statement, the uniform continuity states something like that. For all epsilon greater than 0, there exists, for all y belongs to a b, and in the same time for all x belong to ab, there exists a delta greater than 0 such that x minus y modulus less than delta implies fx minus fy less than epsilon. The difference between this definition and this definition is, this definition is you are free to choose different delta for different x values in that interval. But when a function you're gonna say it is uniform continuous, you can only have one delta to work with all x values in this interval. It is the definition of continuous function. It means something like that. If you take a function value like that, there is also, according to previous extreme value theorem, there exists a minimum and a maximum. If you want to select any epsilon value, let's take any epsilon value, you can partition this y-axis by epsilon. When you partition like epsilon values in this x-axis, you will get at the same time the corresponding intervals of x values, corresponding values of x values intervals. It means you get different intervals for each different set. You can say this epsilon value and this length also epsilon, and you get corresponding lengths from x-axis according to that. So you get a finite number of lengths in x-axis. If you take the minimum length, of these x values, I say delta 1, delta 2 and delta 3 and so on. You can have many deltas as you want, and you take the minimum out of these deltas. That delta you can work with any value, and you can say that the function value is vary. If you can take any value from that interval, let's take x0. If x minus x0 modulus less than the minimum delta, that's value, the function variation should always less than that particular epsilon value. So in that way, you can take on a closed interval in a continuous function, you can take for any epsilon, you can find a delta for work with all values such that fx minus fx0 less than epsilon. This is a very strong thing you need to understand when you're going to prove Riemann integration, because every continuous function on a closed interval is uniformly continuous. This is just a theorem, but this is really what happened inside. If you can partition any epsilon value you can want, the function is bounded in a closed interval, and you can partition the y-axis, and you can get corresponding x values, x intervals in x-axis, and you can take the minimum, and that minimum value will work for every value to satisfy the continuous function's definitions. So take that in mind and move on to prove the Riemann integration. So according to that, a to b, there's a function, and we take some partitions. So according to the uniform function definition, there exists a delta to work with any epsilon such that in that delta the maximum allowable difference between the maximum function value and the minimum function value should be epsilon. It means if you take an interval around some x0 value to delta and a delta, some delta value, in this difference should be less than epsilon. That is we all need, because we need to prove in Riemann integration to exist a partition such that upper sum minus lower sum less than epsilon. So we need to build a good condition to this happen. So we gonna do that like this way. In this way. So we take a continuous function on a closed interval and partition it by a way that this interval should less than that delta value. When we take some partition like that, this value is less than or equal delta, and this value, the minimum value and a maximum value, and the difference should be less than epsilon. We can take any positive value, so I take epsilon by n, which is the n is the number of partitions. Now we can take the upper sum. We can take the upper sum. It is equal to the length I call delta x into mk, and I also take the lower sum. If I take this partition to this difference between those x value to be equal, like equal partitions, I can take this delta x value out. So if we sorry, this sigma sign not here. When we write upper sum minus lower sum, we can take this delta x out and sum up mk minus simple name k. Now that is the important thing. I make this partition in a way that this value in each segment, in each small partition, to be less than or equal epsilon by n, and there is n number of partitions. So we can say that this is less than or equal delta x into epsilon over n. If we can take this value also n and n into, if we take b and a, and we can take n into b minus a, we can make more easier it. So this value should be less than b minus a, and this value should be less than b minus a. So in a way that we can take that this value is less than delta x into b minus a into multiply by n, because this is constant, and epsilon. Surely this part is less than or equal 1, because delta x is the length of this small part, but b minus a is the length of this whole thing. So this is less than or equal 1. This is less than or equal 1. So we can write that this whole thing is less than or equal epsilon. So finally we can conclude that if this function is Riemann integrable, or we can find the area exactly, we can conclude that for all epsilon greater than 0, there exists a partition of AB in a way that upper sum minus lower sum less than epsilon. It means this sum is less than any positive number, or in other words, upper sum equals lower sum. This is the basic definition. If you want to visualize that, simply follow these steps and take any function and partition it to these small values to be less than the particular specific delta to work with every x value in this region to satisfy the continuity function's definition, and try to approach that. This is the basic and the very strong definition of Riemann integration and its proof.